Hey everybody, this is Larry. This is me going Q4 of the maximum good Subtree score. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. Honestly, this one's a little bit weird, only in the sense that we did a very similar problem maybe last week. That's how I was able to get this so fast, relatively. At least I consider it fast, like about 20 minutes. Though I mean, even last week I had the right idea. It's just that the implementation was a little bit awkward. But you know, I was able to nail that down a little bit more, right, for this one. But yeah, but because of that, this is definitely a very awkward problem. Let me pull up the drawing real quick. But the idea is just dynamic programming, and a couple of ways you can do dynamic program for this one for sure. And some of them may time out, some of them may not. So I didn't explore all of them. I only did the one that, which is what I learned from last week. Is just, I think it's the fastest while still being understandable, though you can certainly do it like in a bottom up kind of way. But yeah, but basically the core idea is just dynamic programming. And honestly, I don't think I'm gonna have a good video on this, because in the sense that it requires the proof itself. For me, I YOLO'd, to be frank. Because I was hoping, because it's one of those calculated YOLO of, if this is not the right way to do it, I have no idea how to do it, right? I don't know if that makes sense, or at least like it would take like another hour or two or whatever if there was another way, or you know, given this level of difficulty in general. And the reason why I say that is because if you analyze the complexity, it's very tricky to analyze the correct complexity, or precisely. I mean, there's an easy way to analyze the complexity, but it ends up being like too slow if you just do it like naively. So I don't know how to quite do that, frankly. But I'm just gonna, you know, I explained that's how I do it. So you know, I don't know. Maybe someone in the forums or someone can let me know what is the like a tighter bang on the proof, right? But the idea is that this is a tree, right? And it's not a binary tree, just to be clear, so it could have, like, you know, a lot of funky things. Well, maybe not that funky, but yeah, and they present in a functional way. And the idea is that, okay, well, if you want to get the answer for this tree, we just have to get all the children and then merge them together with the whatever, right? Easier said than done, of course, but yeah. But the key thing to note is that you only have 10 numbers, right? Or 10 numbers to keep track of in terms of like whether, or 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Of whether we use them or not. And what that means is that for each, and because there are 10 digits, 10 things that we care about, there's only 2 to the 10, which is equal to about 1,000, right? I mean, I know it's like 1024, but you know, let's just say 1,000. And not 1,006, because I just have poor handwriting. So you have 1,000, right? You're Gucci. That means that for every node, that just store 2 to the 10 things, 1 for each digit being used, right? Meaning that, okay, like literally you would store, okay, what is the best result if we use none of the digits? Yeah, maybe it's probably 0 because you didn't use any number. What's the best result we only used a 1? I don't know, maybe a 1. Only use a 2, only use a 3, or maybe even like a combination, right? So this is like 1, this is like maybe 1 plus 2, maybe that could be 21, I don't know, 1 plus 2 plus 3, or maybe 1 plus 3, dot, right? And all I'm saying is that if you do the power set of this, you are going to get 2 to the 10, right? And then you have an array of these answers, and there are only 1,000 of them, or 1,024. 2 to the 10 number of them. So that's basically the idea. And then the hard part, maybe, and you know, if you haven't done it recently like I have, then maybe it's a little bit trickier, is that, okay, that means that for each node we want to store 1,000 things, right? So then how let me just actually redraw this real quick, right? So then now the idea is that, okay, but the 1,000 things are related, right? So they're not just like independent things, so they don't get multiplied per se. But the idea then now is that, okay, let's say you have a number of children, you have 1,000 thing here, 1,000 thing here, and 1,000 thing here, 1,000 thing here, right? But the thing is that they're all related in a way such that you can you could just go through them and merge them, right? And what I mean is that, so you have 1,000 things here, maybe not, and you have 1,000 things here. Then now you merge them into what? Also you merge them into 1,000 things, not 1,000,000 things. So then now as a result, now you could merge, after you merge these two result, then now you can merge the next the result of this with the next one, and then merge that with the next one, and then so forth, right? So it's going to be 1,000 items the entire way, or roughly speaking. And the way you merge them is just, you kind of write them out. It's relatively straightforward in a sense, because you have like 1 and 3, and then maybe will give you like an answer, like the best answer is, I don't know, 100. That doesn't make sense, but whatever. And then you have, maybe that's from this node, and then maybe from this node, you have an answer that's like, 2 plus 4 is equal to 6, 2 plus 5 is equal to 20, and maybe even like a 1 plus 4 is equal to 15, right? I don't know, these are random numbers. But then now to merge them, then it is, pretty reasonable, pretty straightforward way of that. Okay, well, you want to try, okay, so we merge this one and this one. Let me change the colors real quick. This one and this one. Then now you have 1 plus 2 plus 3 plus 4. That means that's what we use, is 106. You merge this one with this one. You have 1 plus 3 plus 2 plus 5 is, I don't know, 120, right? But then you can merge this one and this one because that would mean that you're using 1 twice, right? So that's it. That's kind of the core idea. There's some more nuance with there's some more implementation details with given a node. Let's say the node is say like 54, then that means that you break it down into like a 4 plus 5 kind of bit mask kind of thing, and that's really the core idea. And then now we'll go over the code. For this problem, I'm going to assume that you understand and know bit masks. This video is already going to be a little bit long, so I'm going to skip the bit mask explanation. Definitely, there are a lot of dynamic programming problems on Leetcode that are bit mask related, and I have a lot of those videos, so definitely check one of those out and practice and etc. My apologies if you're watching this and somehow this is your first time seeing bit mask, but it's I wouldn't say it doesn't come up that much in interviews and stuff, but in competitive it does come up here and there, enough for you to wanting to learn it, and on Leetcode a lot more, because I guess that's just the difficulty scope, right? And today I'm like a little bit feeling unwell. But in any case, yeah. So then I have a bunch of functions. Here I have like a pre-processed bit mask. So that means that for every number in rows, I just calculate the bit mask of them. Of course, in this, I also have a -1 flag of if the -1 is just for if given this one number, we have the same digit twice, meaning like if you have 11, then you can never pick the number 11 because it already uses the one twice, right? So that's basically the idea. And this bit mask is just given a number x, what is the bit mask of the digits representation, right? And bit mask is just a fancy way of saying like a list of Boolean values in a way, because it's just a list of Boolean values represented as a number, right? Because you can think of each number as like 0 and 1s, and then now zeros and ones, and then you can say, well, this is if the 0th digit is a 1, or the least significant digit is a 1, that means 0 is used. If it's a 0, that means that a 0 is not used, and so forth. And that, you could go through this code. It's just one digit at a time. We order it to kind of flip the bit on, divided by 10, and so forth. Yeah. And then you have this one, which is, this is just creating the adjacency list from the parent down, so that I could get it from the root instead of from the children going up. Just a short way to change it. And then this is and this is the rest of the code. So it's kind of relatively short. So for each node, we set up two things, right? We know that we're gonna have I don't want to use an array just because a lot of the things are not possible. So that's why I don't like setting an array. So I have a map instead. And what this does is that we have, the default is we use 0 of the digits. So you have 0 sum as the answer. Here, this is the pre-processed number. We already got it here, right? From here. It just means that if we're setting the default of, we're using only this node, so only one number, and it's only this node, we set it to the value of the node, right? Meaning if the node value is 34, then we set it so that the bit mask, this is the bit mask. The bit mask is going to have the 3 and the 4 bit flip to true, and then the value is 34. And that's basically the idea. And then now we do the recursion. For every children, we get another map from the children. And then, and this is just to kind of set it up so that we can update, right? And we look at every number that we had so far and every number that we have from the children. And then this is a bitwise Boolean array, if you will, of an AND function, meaning that if there's any overlap, then this will return a non-zero, right? So if it returns 0, that means that there's no overlap, meaning that it keeps the invariant of the fact that we did not use the same digit more than once true. And if we do that, then we have the new bit mask, which is now a bitwise OR, and then we just get the sum of the two components combined, right? So this is like a divide and conquer merging type thing. And and then the reason I did it so that it doesn't change the items thing, but I put it in another array, and then and this is just check the min thing. So if the bit mask is not already calculated, then we just update it. Or if the bit mask we have is not as big as the new value we calculate, we also update. And then we're just going to do this for every child, and that's it. And then for this problem, you're trying to get the sum of all values, where max score is the score for one node. So we just do a for loop, right? We do a for loop. I do the score. We take all the possible values that starts at node I. We take all the max of those, we sum it, and then at the end we remember to mod. The reason why I don't mod every time is just, I don't know, just me being lazy, but because it does overflow, but not by that much in Python. So because you only have n of these, so even if they're big numbers, it's not a big deal. And mod is expensive-ish. I don't know what the trade-off is, or at least I didn't do the math on it. But that's it. Ish. So what's the complexity here, right? I mean, the tricky thing is that this could be 1,000 elements and this could be 1,000 elements. It's not easy to make it possible to have all 1,000 elements, which is because I think it takes like I guess it only takes like 10 elements to have all the bit mask filled, but I don't know. Honestly, I don't know. I know the complexity. Like I said, this is going to be 2 to the n. This is also 2 to the n. There's a lot of cell pruning that makes it a little bit faster, but at the end of the day, it's still 2 to the n times 2 to the n. So it's 2 to the 2n, but for each node, right? And each node is 500, or there are 500 nodes. So it's going to be 500 times a million, which is honestly very awkward for me to kind of, if I wasn't YOLOing, I don't know if I can prove this to you, and I still can. I mean, I have the benefit of doing this video afterwards, and I still don't. So, but that is all I have with this video. I think overall the idea is not that tricky if you did the last week. I mean, I think that's the only thing, right? Is that I don't think this is easy, to be clear. But we also did maybe literally this problem last week. So then it's we put it that way, then obviously it's a little bit easier. That's all I have with this one. Let me know what you think. Thanks for watching. And you can watch me solve a live then contest next. maybe skipped ahead real quick with Q4. Maximum good subtree score. Given an undirected 0 to n minus 1, each node has and its parent. Okay, so you have a tree, you have a parent, you have values. There's a mod thing, so let's mod it out. Mod. Okay. All right. Subtree of nodes. Every digit from 0 to 9 appear at most once in a decimal representation of the values of the selected node. What does that mean? But okay, fine. The score of a sum of the value of its nodes. Subset of nodes within a subtree is called good. Every digit from 0 to 9 appears at most once in a decimal representation of the values of selected nodes. Okay. Can it be the values have the values can have 3 and 4. Okay, fine. The score of a good subset is the sum of the values of its nodes. If subset of nodes within a subtree is called good, okay. The score of a good subset is the sum of the values of its node, okay. Define a max score where maximum score sub u represent the maximum values of a good subset, including u itself and all its descendant. It seems like just dp, right? Return all the sum of values in max score. What does that mean? Oh, okay. So you have to get the max score for each one, and then, I mean, it's just how many trees are there? How many nodes are there? 500. This is just straight up DP then, right? I mean, I don't think there's anything too tricky about it per se. Maybe I say that and then maybe I get eaten, but parent sub I. All right. So I don't know. Right. So for IP in a way, now E of P that would depend I, right? Okay, so then now we have a tree going downwards. Yeah, okay. So then now we just calculate okay, so the node and then the bit mask, but how do I do the math? How do I do the math? Well, how do I spread it across different trees? I guess that's the question. Oh, this is the same thing as the other problem that we did with the DP over the children kind of thing, right? That's too slow though, isn't it? 1,000 for each one. I don't know. Maybe this isn't quite right. Like I said, maybe I am incorrect. Because then now you want to give. When you have 1,000, so each node will have each node doing 1,000 squares. Probably not quite the way that you want to do it, right? How you could do a merge that way, but that's not even that much cleaner or that much faster. Man, today I'm not good. Okay. Is this the is this I don't want, I can't prove it. I don't know if it's another one of those problems where a lot of the things are technically not possible, so it's okay kind of weirdness. How do you merge in a easy way? How do you merge in a way that isn't that isn't that isn't a million n square? Hmm. I don't know, but okay, fine. Let's just say we have okay. Let's just say we have f for some f, right? For children in the sub node, stuff happens. So okay, so f of children. I guess we'll see. I don't know anymore. I don't know if this is good enough, honestly. I feel like I did a similar problem recently, but always get wonky about this. But okay, let's just use an array, right? No, that copy, does that work? The copy of map a dictionary. How do I guess we don't have to, right? We just kind of So good. So if there's no bit overmass, then dot append. Okay. And then at the end, then we go for, oops. Okay, right. Maybe that's fine. I don't know what this loop does. Oh, me running that does. Okay, so we go 0. Okay, so then now just do it for each loop, right? So for I in range to n, score is equal to 0. Score we added by go I. Well, go I returns a map, so then we want max.value or something like this. Okay. Something like that should be fine. I know it overflows in some languages, but this is fine. Okay. Yeah, I mean, I didn't do the base case of using this node, right? So using this node, we want maybe we pause it already. For e in okay, right. P dot append get mask of v, and then just v. Doesn't, I guess the I doesn't matter. Just getting the mask, right? So here what if the number itself has multiple times? Then it just can pick itself then, right? So then, okay, so and also this is wrong, right? Did the parents wrong? But no, I mean, okay, if really 0 doesn't oh, 0 has to this is so awkward, but okay, fine. I guess this is fine actually. Okay, all right, so then now okay, so it cannot be 0, because if it could be 0, that's a really awkward thing, right? Okay, so if C is equal to x mod 10, if -1, otherwise Okay, and then now we do f of, I guess I didn't need to put in a different thing, but anyway, what's it called? Not f, p of node of 0 is the mask, so we just put it this way, and then it's equal to v, which is p of node of 1, something like that. Int, is that not here? Oh. So now we otherwise something like that. Node, what? Int object. Where did I get int object? Did I set it by accident somewhere else? Oh, I said p, so that's why. Okay, fine. I don't know why. I don't even know what p stands for. Honestly, terrible variable names. That's what it stood for. Okay, what is it? 8, 15, 42, 18. The only question is whether it's fast enough, I think. Let's actually cache clear this thing. It doesn't even tell me the time anymore in here. So, YOLO submit. Whew. Is that in the input? That's not an input, right? Okay. So, I mean, if it's in the examples, I would feel way worse because that has happened a lot also. So it's not even like it's, you know. But okay, so I choose a number that's way too big. The answer should be this, which is what, this times this. So this is the parent. So it's this, and then this as a linked list. Okay. So here the subtree is just gonna be itself. Okay. Let's just print it out real quick. Maybe that's too much. You see? Okay, so then now this 0 case is definitely not right. Because it means that we're not using any numbers. So there's something really wrong here in general. Oh, I'm dumb. This is an OR. Larry. How did I get the annoying thing is that I got the inputs or like the examples right, even given that really silly typo. Okay, so that's good. This one, it actually we're not even that far. Okay, so we got this one, that's good. How much time do I have left? I have 18 minutes left for Q3. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, today's contest, everything in between. Stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye-bye.